Hello, welcome to Electrical Circuits part number 13, Resistive Capacitive Parallel Circuit Analysis, or RC Parallel Circuit Analysis. We'll have one branch with the resistor and one with a capacitor, and we'll be at 60 Hertz for our frequency on this. Now we know in a parallel circuit the voltage remains constant, so our total voltage is equal to the voltage at the resistive branch, and the voltage at it's equal to the voltage at the capacitive branch. So we can populate V sub R and V sub C with that 240 volts. Now to find the current at the resistor, using Ohm's law, I sub R is equal to V sub R divided by R. So 240 divided by 30 gives us 8 amps. I sub C is equal to V sub C divided by our capacitive reactance, X sub C. So our 240 divided by 20 ohms gives us 12 amps. And I sub T, as you'll notice, I have the Pythagorean theorem up here. Where in the series circuit we use the Pythagorean theorem to calculate our impedance, we'll be using it to calculate our current in a resistive, or not a resistive, but a parallel circuit. So our current total is equal to the square root of I sub R square plus I sub 2 square. So our 8 square plus 12 square, the square root of 8 square plus 12 square will give us 14.42 amps. Again, you can see there if we tried to add them up, we'd have a total current of 20 amps. So that's why if we're not in a purely resistive circuit, our quick checks in our math do not work, so they're out the door. Now we're going to figure our true power, which is measured on the resistive part of the circuit. So we're going to take our 240 volts and multiply it by the 8 amps at the resistor, giving us 1.92 kilowatts for our true power. Our VARS sub C, our wattless power, is equal to V sub C times I sub C. So the 240 volts times the 12 amps gives us 2.88 kilovars. Our capacitance is equal to 1 divided by, open your parentheses, 2 times pi times frequency times the capacitive reactance. So we'll use the frequency of 60 Hertz and our capacitive reactance of 20 ohms. And that'll give us 132.63 microfarads. And now we're going to be looking for our impedance. Whereas we had to use the Pythagorean theorem in a series circuit to find the impedance, we can use our Ohm's law here. So Z is equal to V sub T divided by I sub T. So 240 volts divided by 14.42 amps gives us 16.64 ohms of impedance. Now our apparent power, volt ampere, is equal to our total current times our total voltage. So our 14.42 amps times our 240 volts will give us 3.46 kVA, or kilovolts ampere. And now we need to find our power factor and our angle theta, our phase shift, our phase angle. And so our power factor is the ratio of the true power to the apparent power. So power factor is your true power divided by apparent power. So we'll take our 1.92 kW and we'll divide it by our apparent power of 3.46 kVA, but we'll put those in standard decimal first, and that'll give us 55.5% of a power factor. And then our angle theta is arc cosine of the power factor, and so cosine to the -1, plug your power factor in as a decimal point, and it'll give us 56.29 degrees. Now remember, we could use this, simply just say 56 degrees angle, phase angle on this. We're not so concerned with the minutes and seconds, we just want the degrees. Now we have all of our calculated values. We're ready to go out to the circuit, make our live readings with our meters, and compare them to their expected values, our baseline, to determine if there's a problem in that part of the circuit. That concludes part 13 of the series. Thank you.